Okay, let's start the talk. So it is my great pleasure to introduce the next speaker, Eunjeong Lee from Chungbuk National University. She's going to talk about on torus orbit closures in flag varieties. Please go ahead.
Thank you for the introduction. And it is my great pleasure to give a talk at the Toric Topology Conference. And I would like to thank to the organizers for giving me this great chance. This talk is based on joint work with Professor Masa in Osaka Metropolitan University and Sanjung Park in Jeonju University. Actually, before going on, I want to introduce the main characters. So there might be a lot of objects will appear during the talk. So I want to introduce some of them. So there are a lot of toric varieties which are smooth or not smooth. And one of the main characters are the torus orbit closures in G mod P. I will explain what are G mod P in 1 minute, but the main characters are torus orbit closures in G mod P, and as you can see, they might be singular. All of them, there are a lot of singular toric varieties can appear. And one most famous example would be the permutohedral variety. I think you already saw the definition of permutohedral varieties, which is the toric variety whose polytope is the permutohedron. And it appears as the torus orbit closure in the flag variety. And also the interesting class of the toric varieties are the toric varieties whose polytopes are the broad interval polytopes Q, V, W. And also another example would be toric Richardson varieties, which are the toric variety can be expressed as the intersection of two Schubert varieties. And also toric Schubert varieties. These are the main characters of the talk. So please remember the name of these varieties. Let's start. What is a flag? Actually, I believe that you already saw the flags during the conference, but I want to remind you the definition and tell you the notations. A flag is a sequence of vector spaces. So here I start with the point and then take the one-dimensional vector space V1 and then two-dimensional space V2, And the full flag is the set of all flags in Cn.
What is the dimension of the maple leaf?
I'm sorry, I don't know. But maybe, so it would be two-dimensional, maybe, because the pole, the flag, the pole are meeting in the ground points. The ground point corresponds to the zero-dimensional zero, the origin, and then you put the pole, containing this origin. So this is the one, it corresponds to the one-dimensional vector space, and the maybe maple leaf is the two-dimensional thing in the flag, and so on. But anyway, the flag can be actually here. I give you the definition as a set of flags, but it can have more structure because it can be understood as the homogeneous space of GLN mod B. And it is a smooth projective variety whose complex dimension is here n times n minus 1 divided by 2. And B is the set of upper triangular matrices in GLN C. And moreover, it has a torus section. So here the coordinate-wise multiplication of T, so C star n on C to the n induces an effective action of this torus on n-1 dimensional torus on the flag variety. And here, actually, in the previous slide, I gave you the definition of the full flag of Lie type A. However, you can define a flag variety in any dimension and any type of flags. So let me introduce them. G is a reductive algebraic group, and T, let me fix a maximal torus T, and then take a Borel subgroup containing T. Then a parabolic subgroup can be understood as a group containing B and inside of G. And if you are not familiar with those notations, then please considering that G is the GLN and T is the set of diagonal matrices inside of GLN, and then B is the set of upper triangular matrices, and P is the block upper triangular matrices having the same block size. Here to define a parabolic subgroup, you have to fix the size of the blocks that you would like to take. And the definition and proposition is the homogeneous variety G mod P is a smooth projective variety, and we call it a flag variety. So in the previous slide, the full flag variety is the case when G is GLN and I take P as the Borel subgroup B. And we usually call that when P is the same as B, then G mod B is a full flag variety. And one another example, extreme example, that is that the Grassmannian that we saw before the coffee break. And when P is maximal, so it means that maximal subgroup, maximal proper subgroup of G containing B, then we call G mod P a Grassmannian. And when G is GLN C and P is P sub D, which is the set of block upper triangular matrices of sizes D and n minus D, then this homogeneous space is nothing but the set of vector subspaces of Cn of dimension D. And in the previous talk, it was denoted by GRD comma N, and GRN comma D, and here I use the notation GRDN, but they are the same. And for the case of the full flag variety of Lie type A, there is a torus section, and there are finitely many torus fixed points. And moreover, there is a bijective correspondence between the set of torus fixed point and the set of permutations. So here Sn is the symmetric group on n, on the numbers from 1 through n. So it is a set of bijections from the numbers from 1 to n to itself. And there is a bijective correspondence. More precisely, for a given permutation W, here I use the 1-9 notation, and because W is a bijection on the numbers from 1 through n, it can be expressed as just listing the image of the numbers W1, W2, Wn. For each such permutation, I have a flag, the permutation flag, WB. So the first vector space is spanned by E sub W1, this coordinate vector subspace, and the second vector space is spanned by E sub W1 and E sub W2, And there is a bijective correspondence between the set of torus fixed point and the symmetric group. And moreover, in general, there is also bijective correspondence between the set of torus fixed point inside of this partial flags and a certain quotient of the Weyl group. So for instance, if I consider P sub D, this is the maximal parabolic subgroup that we saw before, then W upper P can be expressed as the permutation. First D letters increases, and then the last n minus D letters increases. So with this restricted permutations. And actually the symmetric group is generated by simple transpositions. And here I want to introduce some terminologies. For a permutation W, we can always express as it as the product of simple transpositions. And LW, called the length, is the smallest m for which such an expression exists. And in this case, we call the expression reduced. And for simplicity, we usually denote the indices by the list, and we call it a word of W when the corresponding corresponding expression gives you the permutation W. And because there is only finitely many torus fixed points, we can apply a kind of the algebra geometric Moore theory. We call it Bialy-Nikodym decomposition. And the broad decomposition provide us this disjoint union of certain affine cells. So G mod P can be understood as the disjoint union of certain B orbit of the torus fixed point WP, and BWP over P is isomorphic to the affine cell of dimension LW. And for each W, the Schubert variety is the subvariety of the flag variety defined by the closure of this affine cell. And to define the Richardson variety, I need to translate one Schubert variety a little, and then considering the intersection, then we got the Richardson variety. So if you pick two permutations and take one Schubert variety and take the other one, and then the intersection becomes the Richardson variety. Here, W naught is the longest element in the viral group W upper P. And there are some notes. So if you pick the longest element, then the Schubert variety is the same as the flag variety that you take. And the Richardson variety is not necessarily smooth. There are a lot of singular Richardson varieties. However, they are always projective, and the complex dimension of Richardson variety can be computed by subtracting LV from LW. And moreover, because we are taking the B orbit and then the closure, the torus T lives in B, so T acts on the Richardson variety. So Richardson variety has the torus section. And finally, because the flag variety can be understood as the disjoint union of affine cells, the cohomology does not have odd degree. And moreover, the G coefficient cohomology can be generated by the corresponding classes. So we have as G module, there is an isomorphism. And actually, the Schubert variety, because they have a beautiful connection between the geometry and topology and representation theory and the combinatorics, Schubert variety appear in many mathematics. So for example, studying the cup product of those classes is closely related to the Schubert calculus, and it is related to the combinatorics. And moreover, because of the Borel-Yuval theorem, the flag variety appearing in the representation theory too. And today we are going to consider torus actions on sub-varieties of the flag variety, including these Richardson varieties, X, V, W. So let me recall the moment polytopes. Let's restrict our attention for the case when G is GLN. And then we have and also P equals to B. And we have a moment map mu satisfying that each permutation flag sends to a certain inverse, the coordinate corresponding to the inverse of the permutation. And then because of the convexity theorem, the moment map image becomes the convex hull of those fixed points. And we call this polytope the permitohedron. And you can see there is a certain linear relation on those fixed point, on the point W1 plus W2 Wn becomes the same as n plus n times n plus 1 divided by 2. So it lives in n dimension, but the polytope itself is n minus 1 dimensional thing. And here on the left hand side, I draw the 2-dimensional, the P pi 2. And yeah, it is pi 3. So sorry, it is pi 3. And on the right hand side, I draw pi 4. Actually, it is a 3-dimensional polytope. And in general, G mod P is a Coxeter matroid polytope, actually. So it means that the moment map image satisfies certain condition that every edge of the polytope is parallel to EI minus EJ. When you consider G lead type of G is A. So here for the moment map image of the Grassmannian 1,3, actually this is just Grassmannian 1,3 is the CP2, and the moment map image looks like this triangle. And for Grassmannian 2,4, you obtain this octahedron that is hypersimplex. Yes. Yes, you're right. I actually, for each case, G mod P, there is an embedding given by the Plucker embedding, and then I will pulling back the simplex form on the project space. Yeah, actually, that is the same one, I think. Right. But actually, at this only the scaling, it does not, yeah. The size of the polytope actually. Yeah. Non-symplectic toric geometry. Did you say not non-symplectic toric geometry?
So there are many embeddings.
Yeah, you're right. You're right.
As a project orbit.
Yeah. Yes, you're right. That's true. That's true. Yeah, you're right. You're right. Thank you.
Symplectic geometry is actually.
It's very important. Yeah, you're right. Yeah, thank you for the comment. And yeah, as we already saw before, G mod P is not toric in general. However, there are toric varieties. By considering the torus orbit, I pick a certain point. Here, Y is a certain point. And then take the torus orbit. Here, T is the torus which acts effectively. And then take the closure that is called, that I want to denote it by just Y. And then it becomes a toric variety by definition. And one point I want to mention is that permitohedral varieties and toric Schubert varieties, here Schubert variety, toric Schubert by mean that Schubert variety itself has a torus section. And with respect to that maximal torus section given by the left multiplication, it is sometimes bitoric. So I want to call them toric Schubert variety. And similarly, Richardson variety itself has a maximal torus section. And if it becomes a toric variety, then with respect to this left multiplication, then I want to call them toric Richardson variety. And all of them can be obtained as the torus orbit closures. And one another point is that this toric variety, you may wonder which toric varieties can appear, and we can look at the toric variety using the moment map. Actually, Y might not be smooth. However, if I consider the restriction of the moment map, then the convex hull of the torus fixed point becomes a polytope determining the toric variety Y. So mu of Y determines Y as a toric variety. And one interesting question is that, which is unsolved yet, characterize the moment polytope. So what kind of polytopes can appear as this moment map image of the torus orbit closures? Actually, this question is closely related to the representability of the matroid, but anyway, it is unsolved. but one necessary condition for these moment maps says that the mu of y should be the Coxeter matrix polytope. This is the result by Galfan and Serganova. So here I draw some polytope polygons in a two-dimensional space in flag C3. And here on the left-hand side, I got a certain square, and you can see that all of the edges are parallel to EI minus EJ, and moreover, it is indeed appears as the torus orbit closure. However, on the left-hand side, you can see that some edges are not parallel to the EI minus EJ, and it cannot be appear as the moment map image as the torus orbit closure. And the fan, we have been studied the fan of the toric variety, and the fan can be obtained by taking the union of cones in the normal fan of the moment polytope. So the permutohedron. Actually, the permutohedron plays an important role to understand those the torus orbit closures, and we consider the toric varieties like the Schubert variety inside of the Schubert varieties or the Richardson varieties. And here the QVW is a certain convex hull of the point. So here I take the two permutations V and W, and then consider the all other permutations in between V and W, and then take the moment map image under and then take the convex hull, then it becomes a certain polytope, and we call it the Broad interval polytope because here we consider the broad order, and then the all point inside of the broad interval appear as the vertices of this polytope. And the toric variety, here I put some examples. So for the permutation, if I pick the permutation 1, 2, 3 and 3, 1, 2, then I have four permutations in the broad interval. And if you take the closure, then we obtain this rectangle. And here, if I pick the permutation 1, 3, 2, 4, and 3, 4, 1, 2, here I highlight those fixed points. And then consider all the permutations in between those two given permutations, and then take the closure, then we obtain these polytope. And as you can see, it is not smooth. Actually, to be a Delta polytope, it should be simple. However, for example, at this vertex 1, 3, 2, 4, it is three-dimensional polytope. However, there are four facets meeting at this point, so it is not a simple polytope in general. However, for any choice of V and W, the corresponding broad interval polytope support the toric variety. So it means that there exists a toric variety associated to QVW, which is a torus orbit closure. So they form a big class in the torus orbit closures in GMAT P. And here I draw this diagram again, and I want to introduce some interesting result together with Professor Masuda and Sanjong. And if I restrict my attention on the full flag variety case and also lead type A, then the broad interval polytopes here, please, this figure is quite small. However, if I consider the case when V equals to E, then we got this smaller area. And then for those specific cases, we know when they are smooth or not. So the smoothness criterion for those toric varieties has been studied. One direction was proven by myself with Professor Masuda, and the other direction was proved by Get. He considered the process structure of this broad interval polytope to show the other direction. And moreover, even though they might be singular, we can compute the Poincare polynomial of the torus, this toric variety. And moreover, if I consider the smooth case here, as you can see in the diagram, toric Richardson varieties might be singular. However, if I restrict my attention on the smooth case, then any smooth toric Richardson variety is a bond manifold, which appear in Sunjung's talk. Here, bond manifold. So these are the toric varieties whose moment polytope is combinatorially equivalent to a cube, and any smooth toric Richardson variety is a bond manifold. And for the remaining time, I want to talk about our most recent result on the toric Schubert varieties. When Schubert variety become a toric, there is a characterization. So XW, a Schubert variety, is a toric with respect to the T action, if and only if the corresponding permutation is a product of distinct simple reflections. So for example, in S3, there are 6 permutations, and I write down the corresponding reduced words. So for the identity, I have this empty word, and there are S1 and S2. There are one-dimensional Schubert varieties, and there are two-dimensional Schubert varieties. And here, the three-dimensional one is the same as the flat variety. And as you can see, for this three-dimensional case, to write down this permutation, I have to use S1, either S1 or S2 twice, at least twice. So there is no way to express the corresponding permutation using only distinct, pairwisely distinct reflections. However, all the other cases, they can be expressed as the product of distinct, pairwisely distinct simple reflections. So it means that those 5 Schubert varieties are toric. However, the flat variety is not toric. And here is our main theorem. So for a given permutations, suppose that they are both toric Schubert varieties. Then the following statements are equivalent. XW and XW prime are isomorphic as toric varieties. And this is equivalent to saying that their integral cohomology rings are isomorphic as graded rings. So it means that we can say about the cohomological rigidity for the family of toric Schubert varieties. And as you can see, the first item is numbered 1, and the second item is numbered 3, and there is another item number 2 that plays an important role to prove 3 implies 1. Yeah, let me introduce the second item. Actually, the second item corresponds to a certain combinatorial object associated to a word. Suppose that G is of simply laced type, so it means that the corresponding Dynkin diagram do not have double edges. And for a word, we will define a directed graph. So the vertex set is indexed by the numbers appearing in the word. And for the numbers, for the indices K and J, we will draw an edge from I sub j to I sub k if the corresponding Cartan integer is -1. I should write -1. Yeah, for the case of Lie type A, if my word is 2, 1, 3, 4, then I have 4 vertices decorated numbered by 2, 1, 3, 4. And then from left to right, let's find the numbers which are differ by 1. Actually, in Lie type A, the Dynkin diagram of Lie type A are connected only when the numbers are differ by 1. So it is enough to looking at whether 2 numbers are differ by 1. And the first number is 2, and the second number is 1. They are differ by 1. So I will draw an edge from 1 to 2 because I will add an edge from I sub j to I sub k. And similarly, I have an edge from 3 to 2. And finally, I have an edge from 4 to 3. And as you can see, this diagram is exactly the same as this right one. So I do not change anything, but I just reorganize the diagram. And here, for example, if I have 1, 2, 3, 4, then I have this diagram, this directed graph. And it is possible that they are disjoint. So if I consider the word 1, 2, 4, 5, then I got this disjoint union of two path graphs. And here are some observations. Since we are considering a reduced word consisting of distinct letters, GI, this graph, is uniquely determined. Actually, it usually depends on the choice of reduced decomposition of a given permutation. However, in this specific case, GI is uniquely determined up to graph isomorphisms. So we can set G sub W as, just by picking G sub I. And moreover, the underlying graph of G sub W is a disjoint union of thinking subdiagrams of G, because we are adding the edges only when it has a non-trivial Cartan integer. And here is the full statement of our theorem. So the following statements are equivalent. Those two Schubert varieties are isomorphic, and that is equivalent to saying that their cohomology rings are isomorphic as graded rings, and moreover, the corresponding diagrams are isomorphic as directed graphs. And for the case when n equals 4, there are four elements having length 3, and then I draw the corresponding directed graphs. And as you can see, the first graph and the last graph are isomorphic. If you change the numbers appropriately, if you change the number 1 to 3 and 3 to 1, then you got the last diagram. So they are isomorphic as directed graphs, and all the others are different. So it means that there are three isomorphism classes among the toric Schubert variety. And here I want to briefly introduce the proof. So let W be a reduced decomposition, and to obtain the equivalence between one, yes?
Tell us again, so 1 implies 3. Sorry, what are you going to do in the next slide?
Yeah, I'm going to explain.
It says 1 implies 2.
Yes, yes. Yes. Let me write down the items. So one is XW is isomorphic to XW prime. And the second item is the corresponding graphs are isomorphic. Let me say as toric varieties. Here they are isomorphic as directed graphs. And finally, here I have the cohomology ring, integral cohomology ring of two toric Schubert varieties are isomorphic as graded rings. Yes. Thank you. So to show first in the equivalence between first and second, we use the description of the fan XW. Actually, we can explicitly write down the primitive ray vectors of the fan in terms of the using these Cartan integers. And here I put the identity matrix on the left, and then put a certain lower triangular matrix. And primitive ray vectors of the fan are the 2m column vectors of this matrix. Actually, for this specific case, this toric Schubert variety is isomorphic to the Bas-Samuelson variety, and yeah. And moreover, we can explicitly compute these integers. And here a sub jk are the Cartan integers, c I sub j corresponding to I sub j and I sub k. And yeah, we can explicitly compute the fan of this toric variety. And moreover, because this is a band manifold, the subset of column vectors form a cone if and only if it does not contain both j, vj, and wj. It means that vj and wj is a primitive collection for oj. And using this fan description, and as we saw, the primitive relation determines the isomorphism classes, and moreover, the graph G sub W encodes all the data of these primitive relations. So by adding the corresponding vectors V sub ij and W sub ij, then it should be written by certain sum of other vectors corresponding to the edges incoming to the vertex I sub j. So by considering the incoming edges inside in the graph, we can write down the primitive relation, and primitive relation determines the toric variety. So it means that because this graph encodes the primitive relation, graph isomorphic, if the graphs are isomorphic, then we obtain the isomorphic toric variety. It explains the relation equivalence between 1 and 2, and we use the second item. So to prove 3 implies 1, we prove that 3 implies 2. Then we are done, right? If they are isomorphic, then we can say that the cohomology rings are isomorphic. So 1 implies 3 is a trivial direction. And to complete the proof, we prove that 3 implies 2. And we by analyzing the square zero classes, we recover the graph. Actually, we analyze the classes whose square becomes to 0 in the cohomology ring, then corresponds those elements to the sinks of the vertices. So by analyzing the classes inside of the cohomology ring, we provide an algorithm to define the directed graph, and then prove that, if rings are isomorphic, then the graphs are isomorphic. This is the way how to prove 3 implies 2. And then for remaining few minutes, let me add a few more words. So as corollaries of proof, one can check the final conditions. So because we know how to compute the degree of each primitive relation, we can say that a toric Schubert variety XW is final if and only if every edge of the graph has in degree and most 1. So we can we know the final condition, and moreover, we enumerate the number of isomorphism classes of toric Schubert varieties, because we know that there is a bijective correspondence between the set of toric Schubert varieties and the set of certain directed graphs. So we can enumerate the number. And moreover, we can define a similar edge labeled digraph for other lead type. Actually, I have to mention that the previous theorem saying that those 3 items are equivalent, we have to assume that G is of simply laced type. Yeah, this holds when simply laced type. It means that G is of type ADE.
The first 2 are always equivalent, but then the third won't be equivalent.
Yeah, you're right. You're right. Actually, actually, for the case of if I consider the case, for example, G2, then the Hilbert surface H3 appear in the or H2 can H3 can appear, so it causes confusion. It causes the problem. Yeah, you're right.
Similar fruit, similar type of fruit. The Richardson variety.
Richardson.
You proved rigidity of Richardson varieties earlier.
Yeah. Thank you. Yeah, we haven't tried it yet. This is for toric Schubert variety. So, and one can define a similar edge-labeled graph for other lead type. So, and it distinguishes the isomorphism classes, so we can obtain the equivalence between 1 and 2. However, 2 between 3 holds for simply laced case. And I want to mention that Richmond and Slopstra studied the isomorphism classes of Schubert varieties. And however, we concentrate on toric Schubert varieties, so we use a different idea. And finally, Eunjeong, Taekyu Hwang, and Hyun-tae Jang, they proved that for bond manifold, for any bond manifold, they are diffeomorphic if and only if their cohomology rings are isomorphic as graded rings.
There's no dimension restriction on the variety.
For any bond manifold, yeah. There is no restriction on the stage, I think, yeah. And as a future work, as Richmond and Slopstra already noticed, it would be interesting to consider the rigidity problem for smooth Schubert varieties. Actually, for smooth Schubert varieties in GMAT B, we still don't know whether the cohomology ring determines the diffeomorphism classes. However, using our result, we can say that when they are toric Schubert varieties, then the cohomology ring determines the isomorphism classes. And moreover, for another specific case, for the Grassmannian case, there are not so many smooth toric Schubert varieties. Only the product of projective space can appear. So for that specific case, I can say the cohomology ring determines the isomorphism classes. So it would be interesting to consider other smooth toric Schubert varieties in partial flag and the cohomological rigidity. But we still don't know. And there are also a lot of interesting questions in the partial, if we consider the partial flag case. Actually, the previous results are only for, we have been studying the torus orbit closures in the full flag case, but we can extend our site to the partial flag case. So it would be interesting to study the torus orbit closures in partial flag. Yeah, I will stop here. Thank you.